Henry's law is a way to talk about the solubility of a gas in a liquid. And Henry's law is really useful for companies that make soda pops, beers, and stuff like that. And the solubility of the gas is represented by that Sg right there. And that Sg, the S stands for solubility of the gas, and it's measured in molarity, all right, big M. And the solubility of the gas equals K, which is called a Henry's law constant. And the Henry's law constant depends on the solvent, so water has its own K value. If you had ethanol, it would have a different K value. But then P is the interesting. P is the partial pressure of the gas above the liquid. And as the pressure of the gas over the liquid goes up, the solubility goes up. On the other hand, if the partial pressure of the gas decreases, the solubility decreases. If you open a can of pop, all right, you're taking a high pressure can of pop. The inside is pretty high pressure, and you're essentially just lowering the pressure down by opening up to the outside. So as the pressure is lowered, the solubility of the gas is lowered, and the gas starts to escape from the liquid. So you have that very satisfying sound effects not necessary, no, but that sound that happens when you open the can of pop that people then think, oh yeah, this must be fresh. All right, well, really it's just Henry's law. You're lowering the partial pressure of the gas, and so the solubility of the gas goes down and the gas escapes, making that cool sound. This is an example of a K constant. This is for oxygen. Oxygen and stuff dissolved in water has that 1.66 times 10 to the minus 6 molar per millimeter of mercury. So you can actually use this. If you multiply it by the partial pressure of the oxygen in there, you can find the solubility of the gas.
When a can of soft drink is opened, a whooshing sound is heard, and the solution begins to release bubbles. The escaping gas is carbon dioxide. Henry's law explains why the gas leaves the liquid only after the can is opened.
In the can, you have a high pressure, like you don't want to shake it up and stuff like that, or else it goes crazy when you open it up. So you have a high pressure, so you have a high solubility. You get a lot of carbon dioxide in the Diet Coke in this case. But then you pop the top and you even pour it into a glass. Now the partial pressure has gone way down. You're going from a high pressure can to a regular 1 atmosphere room environment. And as the pressure goes down, the solubility goes down. So all of this gas, which was dissolved in the Diet Coke or whatever, starts escaping. And you can see that kind of hissing kind of sound that comes out and stuff like that. The industries love that because usually it makes people think that it's refreshing and stuff like that. But you now know it's just all about Henry's law. Woohoo! Here's a question. After a can of Diet Coke is removed from the refrigerator, opened and left to stand a while, which of the following best describes the changes that cause the soda to go flat, lose its CO2? All right. So the first one, lowering the CO2 pressure over the solution and raising the temperature. Well, yeah, that makes sense. Lowering the CO2 pressure over the solution. Possibly. Lowering the temperature, increase in salt content. Well, definitely answer D is flat out because there is no salt being answered, all right? You're not really lowering the temperature either because it was in the refrigerator. So if anything, you're increasing the temperature, all right? So the options here are lowering the CO2 pressure over the solution and raising the temperature. Or you can think about it as just lowering the CO2 pressure over the solution. Because it's warming up, the temperature is going up, so the CO2 has more action. And of course, you're definitely lowering the pressure by opening the can. So I would argue that answer A is the best. You're not just lowering the CO2, which is really what Henry's law is all about. And you're lowering it because you're opening the can, the new pressure is less, so the solubility goes out, but you're also raising the temperature, and that has to be part of it. As you increase the temperature, you'll have more of the gas escape and stuff. We saw this back in the gas law. I think answer A is probably the best. C, once again, is not right because you're not lowering the temperature. You're raising the temperature by letting it sit at room temperature. And finally, there's nothing to do with salt, so that would be just a silly answer. Generally speaking, the solubility of solid solutes in liquid solvents will be increasing. And we saw this picture earlier. And again, most compounds, the solubility goes up as the temperature goes up. And that's a generally good rule of thumb. There are exceptions, though. We saw that cerium sulfate thing down below. That would be an example of a compound that actually decreases its solubility with increasing temperature. For gases, on the other hand, though, usually it's the opposite. Raising the temperature lowers the solubility. So back to that Diet Coke example that we left sitting in room temperature, we basically were raising the temperature on it. And the solubility actually decreases with increasing temperature. As the gas molecules have more energy, they're more likely to escape and stuff like that. Warm lakes have less dissolved oxygen than cool lakes, all right? Because the warmth tends to make the oxygen get out of the water.
The vapor pressure of a liquid depends on the ability of the liquid's molecules to break intermolecular forces and escape into the vapor phase. A molecule can escape only when it has enough energy and is at the surface of the liquid. When a non-volatile solute is added to a liquid, some of its molecules occupy surface sites in the liquid, displacing volatile solvent molecules. Because fewer solvent molecules get to the surface, fewer can escape, and the vapor pressure of the solution decreases.
Colligative properties are the properties that solutions will exhibit, and it includes things like vapor pressure going down, it includes the boiling points increasing, melting points decreasing, osmosis. And to understand them, we're going to first of all need our new concentration units, and that's cool. But we also need to talk about a little bit more about what's happening in the liquid-vapor equilibrium. And in the last chapter, we looked at how liquids always have a little bit of gas over them, which is the vapor pressure, and vapor pressure changes can be used to describe the difference in boiling point. So if you change the external pressure, you change the boiling point of the liquid, blah, blah, blah. And no big deal. Now, both of these flasks are closed flasks. So the liquid and the gas above it, the vapor pressure, they get in equilibrium pretty fast. If you put a solute in with the solvent, and these solutes, by the way, are non-volatile, which means they don't easily turn into a gas, by the way. But anyway, the solute molecules act as like blockers. And I always use the idea like at a nightclub, they'll have like pretty tough looking people outside the door and, only some people can get in. But if you really, really want to get in, you can probably go through the side door or something like that. So solute acts kind of like a bouncer at a nightclub, all right? And they're keeping the liquid molecules from going into the gas phase, all right? They're blocking the equilibrium. Now, once they get in the gas phase, it's easy to go back to the liquid phase. The blockers don't have anything to do with that. But those solute molecules are keeping the liquid molecules from getting into the gas phase. And we're going to use this idea to better understand where the colligative properties come from. But you can see probably even right now that if the bouncer solute molecules are keeping liquid from going into the gas phase, then your vapor pressure will be lower in a solution than it will be for the pure solvent. Hint, hint for something coming up. This was studied for quite a while, and a guy named Raoult, and I hope I'm saying his name right, I probably am not, but anyway, he came around and realized that, interesting, the mole fraction of the solvent is actually proportional to the vapor pressure of the solvent. Now let's talk about that a little bit. Most of the time in these problems, water will be the solvent. Not always, but a lot of times. As the mole fraction of the solvent goes up, the vapor pressure of the solvent over the solution goes up as well. And what he did then was he came up with this expression right here. And people refer to it as Raoult's law. And it basically says that you have some vapor pressure of pure solvent. And the little 0 right there means vapor pressure of pure solvent. So there's actually tables that you can look up, and I'll show you some of these here in a little bit, that are actually vapor pressure values of solvent at different temperatures. And if you're making a solution, then you have to start thinking about mole fraction of solvent. In a pure solvent, the mole fraction would equal 1, no big deal. But in a solution, that mole fraction will be a number less than 1. So the vapor pressure of the solvent in the solution is this thing right here. And the vapor pressure of the solvent in the solution will be less than the vapor pressure of the pure solvent, P0. And all this is saying basically is that in a solution, your vapor pressure is going to be less, which is what I was babbling about in the last slide. So Raoult's law, which is sometimes referred to as vapor pressure depression, which means the vapor pressure is lowered. The vapor pressure is lowered in a solution relative to the pure solvent. And you can calculate how much lower it is if you know what the vapor pressure of the pure solvent is and you know the mole fraction of the solvent in the solution. Let's do an example of how this works out. Earlier, we did a problem where we had 62.1 grams of ethylene glycol and 250 grams of water. And when we went through the problem, we calculated that the mole fraction of the ethylene glycol was 0.0672. Well, we can use all this information to calculate the vapor pressure of water in the solution at 30 degrees Celsius. So we have here a solution. It's ethylene glycol plus water. And we're going to need the vapor pressure of the pure water. And this number right here, which is 31.8 millimeters of mercury, that's the vapor pressure of pure water at 30 degrees Celsius. So if you have pure water and you heat it to 30 degrees Celsius, the vapor pressure is 31.8. However, in the solution now, the ethylene glycol is going to be our bouncer, our blockers, all right? And they're going to keep the water from going into the gas phase. So the final answer here is going to be a number less than 31.8. And how you calculate it is that first you need the mole fraction of the solvent. And this part is a little weird because most of the time we're interested in the solute, but this is actually one time you need the mole fraction of the solvent. We saw earlier mole fraction of ethylene glycol, 0.0672. There's only two components, ethylene glycol plus water. So together the mole fractions always equal 1. So 1 minus 0.0672 equals the 0.9328, which we might have talked about before, but it's important to highlight again. That's the mole fraction of the solvent in the solution, and that's important. We're going to take that number and multiply it by 31.8, and the answer that you get, 29.7, that's a smaller number than 31.8. So what's this is saying here is that in the ethylene glycol solution, the water's vapor pressure is only 29.7. It was 31.8 millimeters of mercury in pure water, but because solute's there, the ethylene glycol, it's blocking the water from getting into the gas phase. So the vapor pressure has gone down in the presence of ethylene glycol. Vapor pressure depression, the idea behind it, that the vapor pressure goes down, we're going to use that in the other colligative properties. Raoult's law has some kind of cool uses for it sometimes. Mathematically, it's pretty easy to do, but you have to remember to use mole fraction of solvent, and you have to remember that you will need the vapor pressure of the pure solvent at that temperature. So here's a question you might see that's related to Raoult's law. We have 0.0400 moles of iodine, 10.1 grams, in 1.96 moles of carbon tetrachloride, 300 grams. CCl4 is very nonpolar. Iodine is nonpolar, so they make a good solution because their intermolecular forces are close to each other. So given the fact that the vapor pressure of pure CCl4 is 504 millimeters of mercury at this temperature, 65 degrees Celsius, what's the vapor pressure of the CCl4 over this solution? Okay, so in this kind of problem, we're going to use Raoult's law, and we're going to calculate the vapor pressure of the solvent in the solution. And that's going to equal the mole fraction of the solvent, and that's important, times the vapor pressure of the pure solvent at that temperature. And if you read through that data, 504 millimeters of mercury, that's the vapor pressure of pure CCl4 at that temperature. That also means that the answer we're going to calculate here, the vapor pressure of the CCl4 in the solution, the answer will be less than 504. Raoult's law is always about vapor pressure being lowered. You'll never have a vapor pressure equal to or greater than, and that's going to be pretty important, as we're going to see. So in this problem, what we need to do is we need to first of all find the mole fraction of solvent, and that's mole fraction of CCl4. So we'll take the moles of CCl4, 1.96, and divide by the total moles. So we'll divide 1.96 by, parentheses, 0.0400 plus 1.96. That's going to give us the mole fraction of the solvent. And we'll multiply that number by 504 to get the answer. And again, right away, it's not going to be the same as 504 because the vapor pressure is going to go down. It's also not going to be equal to or greater than 504 because the number is going to go down, not go up. I would suspect is going to be 494. Usually the vapor pressure doesn't make it go down that much, and I kind of think that might be the case. But let's do the math, all right? And what do you know? Instructor knows everything in it. Yeah, I just wrote this problem, okay, so I knew it. But anyway, I digress. First thing to do, find the mole fraction of the solvent, and that's this 0.980 number right there. We're going to multiply that by the vapor pressure of the pure solvent, which is 504. The answer will be less than the vapor pressure of the pure stuff. 494 millimeters of mercury looks great. Raoult's law in the previous example had what's referred to as a non-volatile solute. So what that means, like in the last example there with iodine doesn't have an appreciable vapor pressure. It's a big molar mass compound, and usually big molar mass compounds don't have vapor pressure. However, sometimes both solute and solvent will be volatile, and it's important to talk about how you make this work. So if you have a volatile solute and a volatile solvent, which means they're easy to get into the gas phase, you need to use a slight different version of Raoult's law, and that's right there. And in that example then, the mole fraction is going to be equal to the mole fraction of the first component times the vapor pressure when it's pure first component, plus mole fraction of the second component B times the vapor pressure of pure B. And if you have three components, you can add another one, etc., etc. Let's look at an example. Heptane and octane are both essentially fuels. And octane, which is essentially gasoline, is a liquid. Heptane is also a liquid. So those are the values, the P0 values, those are the vapor pressures for the pure solvent, for pure heptane and for pure octane. And let's say that we mix heptane and octane together such that the mole fraction of the heptane is 0.15. We can use this information to calculate the total vapor pressure of the system. So mole fraction of heptane would be like X size A, the mole fraction, and we would multiply it by the vapor pressure of pure heptane. That would be like 31 torr, all right? Then mole fraction of octane, the other piece, well, if there's only two components, then one minus the first gives you the second. So 0.85 we're going to see is the mole fraction of the octane, and we'll multiply that by the vapor pressure of pure octane, which was the 11 torr number. We're going to add all these pieces together, and then we'll see what's all going down. In this problem, what you want to do is, first of all, this is a two-component system, and if you add the two components together, the mole fraction is always equal to 1. So if the mole fraction of heptane is 0.15, octane will be 1 minus 0.15, or 0.85, and that's kind of cool. Then we're going to use this expanded, if you will, version of Raoult's law, where we have both heptane and octane components. Mole fraction of heptane times the vapor pressure of pure heptane plus mole fraction of octane times vapor pressure of pure octane. And we'll add all this stuff together. So this is kind of a plug and chug problem. 0.15 times 31 plus 0.85 times 11. Make sure the vapor pressures are in the same kind of units. This comes out to be 14.1 torr. So this solution of octane and heptane should have a total vapor pressure 14.1 torr.